All right, we'll go ahead and get started. The sooner we get started, the sooner we're done. So today we're just going to kind of go over clay mineralogy. So when we're talking about like soil structure, it is the soil colloids that are going to give us our charge. And so in this clay or humus particle, we have these negative charges. And I kind of mentioned this as we left out on class on last week. This is these clay particles and these colloids are where we get our charge from. They have a large surface area. They have both positive and negative charges, but the overall net charge is going to be negative. I know I might have covered some of this if you're taking AGR in 2000 this semester. But so like when I think about colloids, I'm thinking about like a colloid is something that stays in suspension that doesn't necessarily settle out. So like fog or smoke, like you can see it as a whole, but you can't necessarily pick a piece out. Like I cannot pick that little piece out of that suspension, whether it be in water or in soil or in air. And so this kind of goes along in with the diffuse double layer. And so here we have our soil colloid. We have all these cations that form this double layer. And then next in our bulk solution, we will have positive and negative. So we'll have cations and anions in this solution. And so what this is kind of like trying to shuffle into a concert. And so it's not just very uniform. There will be some movement in between where we might have this this positive cation exchange with this one. And then this one might exchange with that one. And then they might exchange back off again. On some of these positive sites that might be in here, we would have to have a movement of this one into here, and then maybe possibly over to here, and then be attached to this positive. And so kind of like at a concert, you know, everyone's not always perfectly square next to each other. Or we're kind of moving around. One person might get ahead a little bit, one person might lag behind, or you might try and walk up real fast. You want to go get to something, but this is constantly moving. And this diffuse double layer will expand with temperature. So like right now, outside with the temperature, the soil temperature being cold, this would be very small. But once the temperature warms up, this would open up more, and there would be more room for these exchanges to happen. We're primarily concerned with the silicate clay minerals, and we have two basic kinds. We have a 1-to-1, which is kaolinite, and so kaolinite is one layer of tetrahedral over a layer of octahedral, and they're bound very tightly. They don't move very much. You can kind of think about this like if you've ever seen red clay, like on a baseball field or a softball field or a roadbed or a house building. Like the foundation that they build, like the pad, and that soil stays very tightly packed together. That's what you would think about when you think about kaolinite. And then we have our 2-to-1 clays, which are going to be more like smectite and vermiculite. And those, as you'll see later, they expand a little bit. So you would not want to build a house or a roadbed on a smectite or a vermiculite. The types, we have crystalline and then non-crystalline. You'll probably be mostly dealing with crystalline, and you might get into some, if you ever go have a job in, let's say, Alaska, kind of in Washington State or something where they have a lot of volcano activity, Hawaii. If you get a job in Hawaii, that'd be awesome. But then you would deal with these aliphanes and amogalites because andesols are from volcanic origin. So unless you're around volcanoes, you probably won't deal much with this non-silicate structure or non-crystalline silicates. Next we have aluminum and iron oxyhydroxides. You might see this in let's say Georgia, where you see some of that red clay. Maybe in Brazil. Brazil has a big problem with that, with these oxasols. They're highly weathered There's nothing left there but just a basic shell of aluminum and oxygen and hydrogen in the structure. And then finally our organic and humus fraction. And so these have a high water holding capacity with both positive and negative charges, the CEC being the negative, the AEC being the positive. But overall, the net charge is always negative. Each of these silicate clay structures are made up of two layers, one being the tetrahedral. So we have tetra, meaning 4. And then you can think about that silica 4+ is typically the central ion in there, or the atom. And then in the octahedral layer, you'll see in just a moment that we have 6 oxygens, and so it's basically 2 tetrahedron that are kind of bound together, overlapping each other, with aluminum or magnesium as the central ion. So here is our tetrahedron. We have 1, 2, 3, 4 oxygens with our silicon as our central atom. Next we have down here is our octahedron. So 1, 2, 3, 4, 5, 6 oxygens with either aluminum or magnesium as our center ion. And this shows you a 2-to-1 clay structure. So we have 2 tetrahedrals, 1 octahedral, stacked on top of each other. I like to consider this like the peanut butter sandwich. Sometimes these structures can be really hard to see. It took me a moment to see where this was. If you were to flip this upside down, you can see that now this basal oxygen or apical oxygen is here. One of those basal oxygens, and then our tetrahedron. And if you look over here, you can see the tetrahedron right there. To me, this makes it much more simple for me to see that. Our tetrahedral, octahedral, and you can see where the bonds are happening right here with these oxygens, and hydrogen in between there. So a 1-to-1, 2-to-1, 2 tetrahedral, 1 octahedral. Important to know about kaolinite is that it has a low CEC. And so CEC, if you have a low CEC, you can kind of think about it like having a small cup at a fast food place. If you get the small cup, you have to go back and refill it up, right? You can only hold so much. So kaolinites have a low CEC, but they can be productive. So you may have to spoon feed these soils in order to get your crops to grow, but it is possible. And as I mentioned, building and roadbed, because it has that structure that lays on top of each other. The force of attraction in between these two layers is so tight that they just won't shift. However, if we have a 1-to-1 on top of a 1-to-1, it is possible to have some water but not much, and that's why they don't shrink and swell. The hydrogen bonds in between these two, though very little water and very few cations can be attached in here because those bonds are so tight and tightened down, and they just stack on top of each other. So you're talking 1,000 sheets to get a piece of clay, right? We're talking scanning electron microscope. That's how small these clay sheets are. Next, we have our silicate clays, which are going to be expanding, our smectites, montmorillonite. You might hear those used kind of interchangeably. Montmorillonite belonging to the family of smectites. A new term here is going to be isomorphic substitution, and we'll go over that in just a minute. But just know that in the tetrahedral, silica will be replaced by aluminum, and in the octahedral, aluminum will be replaced by magnesium. And also that we have a much greater CEC compared to kaolinite. So these are, they can be fairly productive soils, but they're also going to cause you some problems. So we have to manage them a little bit differently. So here we are. We have a 2-to-1 on top of another 1-to-1, and because the attraction, the charge is spread out so much over this area, we're talking nanometers, maybe even angstroms, the size of this. Water can get in between those two sheets and sort of move them apart a little bit. It will push it away just a little bit. And when they expand, cations can then move into, and when they dry, they will sink back down. So they can hold on to cations on these charges right here, on the edges, on the outer edges. One important type of non-expanding silicate clay are going to be micas, such as like illite. And so what happens, we have that 2-to-1, we have a 2-to-1 on top of a 2-to-1. Water enters and does open that up just a little bit, and potassium then enters in to that little space, and when it dries, boom, the potassium gets fixed in there. And so potassium and ammonium are both about the same size, and so you can also have some ammonium fixation in these types of soils. Good? Okay. Next we have chlorites, and this octahedral layer takes the place, and it just kind of cements that down in there, like it locks it into place. This extra octahedral layer binds these two tetrahedral layers together, and it cannot expand anymore. All the charge is tightly binding those two 2-to-1 sheets together. Oh, why? Okay, cool. All right, so here we go. You can see all these together. You will probably have to identify these on a quiz or a test, that this being a 1-to-1. This would be a smectite. Vermiculite is a 2-to-1 with the water molecules entering in between it and other ions. And then our micas, you can think about the K being trapped in between those layers. And then finally our chlorites. What's important to know about this here is to understand some of the net charge that is going to be associated with our different colloid types. We see at the top we have our largest 3, well actually 2, being those smectites and vermiculites. Also remember, smectite and montmorillonite are kind of the same thing. So we will have a large CEC, or the big cup. We will have a big cup to put more of those nutrients into, and the soil will hold on to them. Our micas and our chlorites, remember, they're the ones that don't expand. So no expansion, no CEC. Micas and chlorites do not expand, and look at the CEC. Smectites and vermiculites do expand, and look at the CEC. Kaolinite does not expand, low CEC. So non-expanding clays, no CEC, or very little CEC. Expansion allows for greater cation retention. Not so much that you need to know about gibbsite and goethite and humus, but also look at the CEC of our organic matter. So if we have organic matter in our soils, we're also going to increase our CEC. All right, just to talk about the aluminum and iron oxyhydroxides, there is no tetrahedron. This was formed with just aluminum. These are going to have a strong anion absorption. Aluminum is a 3+, and that charge will be able to extend out, and we will have, let's say, a phosphate be attached to this hydroxyl group because there's a strong charge on that aluminum. So like in Brazil, they have a problem with, they'll throw lime at it, they'll throw lime at it, they'll throw lime at it. All of this aluminum will end up neutralizing some of that lime from the other way. Remember, when we add lime, we're trying to increase the alkalinity, neutralize the acidity. Just that there's so much aluminum left that it actually neutralizes the lime and doesn't necessarily change the pH. So then we apply phosphate, and that phosphate is now tightly bound to this aluminum, and you can throw phosphate at it all you want to. Again, it neutralized all the lime, so it's going to also be able to absorb most of that phosphate. So they have a big problem with anion. They have a big problem with nutrient deficiencies for their anions, nitrate, phosphate, sulfate, things like that. Here's a look at our humic structure. A lot of stuff going on there. Not necessarily important to know, just that we're going to have some of these functional groups. Well, we have a carboxylic. I'll show you in the next slide. Are you going backwards? I'm pressing the back button. That's why. All right. Lots going on here, both positive and negative charges throughout this organic material, but that the overall charge is negative. So there are two sources of charge, one being isomorphic substitution. One being isomorphic substitution, where we have this substitution for silica with aluminum replaces silica in the tetrahedral, and then magnesium replaces aluminum in the octahedral. And so you can kind of think about this like a bank account. So if you had $4 in there, and then you pulled $1 out, this aluminum replaced that, the charge change would be more negative. And we'll see this here. So oxygen being worth -2. So the overall negative charges on this are 8. There are 4 oxygens, -8, and then a charge of +4. So the overall net charge on just this single tetrahedron is -4, right? Simple math. It's adding and subtracting. Next, if we substitute, if we were to substitute an aluminum 3+ here, then the overall charge would be -5. Does that make sense? Because we had +4, -8, and +3 would be -5. We're gonna look at this more in depth in just a moment. Then for our octahedron, we have 6 oxygens, so our negative charges are 12, and aluminum 3+, so our overall net charge is -9. And so if this were stacked right on top of each other like a 1-to-1, the net charge of this would be -13. Okay. In the tetrahedral and the octahedral, we have 2, 4, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. 17 oxygens, each worth -2. So our overall charges, or our net charges, equal 34. We have, in the tetrahedral, we have silica worth +12. In the octahedral, we have aluminum +12. So our overall charges for positive are 24. the overall net charge on this would be -10. On the left, we have our standard silica in the tetrahedral, aluminum in the octahedral. We have a 2-to-1. Here's our tetrahedral, here's our octahedral. If we add up all the charges, across the top we have 7 oxygens worth, -14. Our silica are worth 12, we have 5 oxygens, 5, 7, and 12 in the middle. So the overall charge on that, I'll let you catch up in there. So the way we determine that, 7 oxygens, each worth -2. We have 14 negative. Silica times 3 plus 4. Silica plus 4 times 3 is 12. We have 5 oxygens worth -10. Aluminum worth plus 12. -10 plus 12, -14. And so the overall net charge on that is -12. If we just had a standard silica and aluminum 1-to-1 clay, 2-to-1 clay, the net charge would be 12. If we add in the isomorphic substitution and we substitute aluminum for silica in the tetrahedral and magnesium for aluminum in the octahedral, and we start doing this math the same way we did the other one, we'll find that the net charge changes. We get 10 more cation exchange sites. And this all happens during the formation of this clay mineral. It's not like we can go out to the field and just apply a whole bunch of magnesium hoping that it would substitute for the aluminum and change the permanent charge of our soil. The way that it was made, whether we have an aluminum or a silica, and this could be interchanged. Once it's made, it's made. That's why it's called permanent charge. Jacob, do you remember the 3 sources of pH-dependent charge from class?
Organic matter.
Okay, we got functional groups of organic matter.
I got it written down.
Okay, so the 3 sources of pH-dependent charge: functional groups of organic matter, aluminum and iron oxides, and broken edges of clays. Aluminum and iron oxides being this. So as we change the pH in this system, we will start to affect how this aluminum reacts in accordance with that system. We probably won't go into that. I'm more concerned with understanding pH-dependent charge on the functional groups of organic matter. 3 sources of pH-dependent charge: functional groups of organic matter, aluminum and iron oxides, broken edges of clays. So it's not so much important that you know what the functional groups are. Like, this isn't organic chemistry. But just understand that the changes that we're talking about are going to happen right here with this alcohol group on the end of this functional group. Copy of. All right, so we're still talking the same thing. Three sources of pH dependent charge. Three sources being functional groups of organic matter, aluminum and iron oxides, broken edges of clays. This was actually the student version. And then I copied some notes over it. It wasn't very kind. So we have these functional groups. Next. So in the context of ag, typically what we'll do is we will grow our crops at the end of the season, we'll harvest it, and we'll typically put out lime. Sometimes it might be right after harvest so that we can allow the lime to react over the course of the winter, and then we may take soil samples in the spring, and then we don't have to put as much lime out, and then it'll give it time to react. So we add lime, we increase the pH of our soil, and when we increase the pH in adding lime, we increase the hydroxyl concentration, and we'll go over this when we do pH. So now we have these extra hydroxyls in soil solution, and because soil is pretty much all of life, is all trying to reach equilibrium, we have a greater negative charge here in these hydroxyls that are looking for a mate, they're looking for a friend. So y'all will probably have to write this down on a test. So listen to what I'm saying, catch the key words, condense it down into your own. Add lime, soil becomes more alkaline, the hydroxyl concentration increases. And this may be the change in pH from 5 to 6. Or it could be from 5 to 7.5. But just understand that when the pH increases, the hydroxyl concentration increases. In order to meet the equilibrium, hydrogens will dissociate from the functional groups of organic matter, bond with the hydroxyls to form water. I'll run by that again while you're writing them down. So we add lime, increase hydroxyl concentration. Because these hydroxyls are looking to be in equilibrium, the hydrogens will dissociate from the functional groups of organic matter to form water. Now we're talking about like a molecule of water, not like a glass of water or a lot of water. We're talking about like Avogadro's number, one of those 6.02 times 10 to the 23rd. Very small amount. This now leaves a negative charge where the hydrogens were once all part of this functional group of organic matter. When we have these extra negative charges here, we can now adsorb or hold on to at least one charge of a cation. Let's say potassium. We can hold more potassium and more potassium and more potassium. Next, over the course of the growing season, so we've gone all the way around. We've harvested, we've added lime, increased our hydroxyl concentration. They need to be in equilibrium. Hydrogen dissociates from the functional groups of organic matter to form water. Next, we're into the growing season, and we're applying fertilizer, and our soils are becoming more acidic. We'll actually go over why they're becoming more acidic in this class. For now, soils become more acidic. We have an increase in hydrogen concentration. We have these hydrogens in solution, in soil solution, and they need to be in equilibrium. Why is that? I'll have to make sure I get you all the right slides for this. There was an animation. we're going to add hydrogens into the soil, right? My animation didn't work. I spent a lot of time working on that animation, so I'm a little upset about that. So we have these hydrogens in soil, and because these hydrogens are now looking to be in equilibrium as well, and so are these oxygens on the functional groups of organic matter, the hydrogens will now associate with those oxygens, or protonate. And so now our charge has changed back to neutral. So as our pH increases, our CEC, does it go up or does it go down? It would go up, right? Because when we add hydroxyls, the negative charge, it increases. When our soils become more acidic and the hydrogen concentration increases, we now have this neutralization. In some cases, this hydrogen that's in the soil solution that's still trying to be in equilibrium, like these hydrogens need to go somewhere. They're looking to be balanced. That hydrogen may associate with this hydroxyl on the end right there and cause a positive charge that will be protonated. And now we can hold on to more anions. And so this is what happens in our soils that have organic matter in an acidic situation, or our aluminum and iron oxides. They can become protonated. And now you can hold on to an anion such as nitrate, sulfate, phosphate, not so much chlorine, but that we would be able to hold on to those. I'm super upset about that. Spent a lot of time working on it. Let's see if it works here. All right, so now we have all these hydrogens, and we've applied fertilizer. Our soils have become more acidic. The hydrogens then associate with the hydroxyls. This also changes the pH of this soil, right? But everything is neutralized back to where it was before we added lime. More hydrogens are added to the soil from reserve acidity. And we have the potential to protonate these functional groups, and now this becomes positive. But remember, now this is going to change very quickly, because once the hydrogen concentration lowers here, this hydrogen will try to get back into equilibrium, and then we'll try to find some balance. All right, I think that's all I got on clay minerals. That's going to be it for the day. Have a good weekend.